Preview.
Kirchoff's laws. Kirchoff's laws has two laws. First is the current law. Now, current flow is a flow of quantity. Ergo, if we have a certain point here, let's represent this as I1, I2, this I3, and I4. Now, the sum of all current entering is now equal to the total current leaving, or the total current entering minus the total current leaving is equal to 0. The second law is the voltage law. Now let's have this sample circuit. Let's represent this as V1, V2, and V3. And let's represent the source as V. Now in a closed loop, the summation of all voltage sources is equal to the summation of the voltage from 1 to 3, given the circuit. So V is equal to V1 plus V2 plus V3. Or the voltage gain, which is the source, is equal to the sum of all voltage drops distributed to the electronic components. Now let's apply this in a sample circuit. Now this sample circuit can be solved by merely using the Ohm's law. Get the total resistance and use the voltage divider theorem, use the current divider theorem to find the current of each component. But what if it changed something? The same resistor, but let's add a voltage source at the second branch. Now let's represent this at 12 volts, 5 volts, 3 ohms, 4 ohms, and a 2 ohm. And let's represent the 3-wire node as node A. And let's assume the current flow. Now, in a resistor, the conventional flow, I always enters the positive terminal of the resistor. So, since we have now polarities of the resistor, let's represent the left branch as loop 1. At loop 1, let's represent the current and the entering loop as the sign convention for all the components. So negative 12 plus 4i3 plus 3i1 is equal to 0. Let that be our first equation. At loop 2, 5 minus 4i3 minus 2i2 equals 0 for our second equation. Now at node A, let's represent our current law. The current entering is I1 and I2, and the leaving current is I3. So I1 plus I2 equals I3. That's our third equation. Now substituting the current law, equation 3, to equations 1 and 2. By substituting 3 in equation 1, we can get a fifth equation with I1 and I2 as variables. Also in equation 2, we also have another equation with variables I1 and I2. Now we now have two equations and two variables, which can be solved simultaneously. If you combine 5 and 6, so we multiply the equation by 3, and the other equation by 2. We can cancel the variable I2, and we only have variable I1. So we can get I1 as 2 amperes. Now using the value of I1 on our equation, we can get I2. And I2 is equal to negative 0.5 amperes. Note that the negative means that our assumption needs to be in the opposite direction. Now using the third equation, our current law, I1 plus I2 equals I3, we now have I1 and I2. Now we can get I3, which is 1.5 amperes.
Hi there, I'm here to discuss to you about superposition theorem. So first of all, what is superposition theorem? Superposition theorem is another way of solving complex circuits with a simpler approach. It is not to use one source at a time in solving electrical parameters of a particular electrical component. So what are the steps in solving circuit problems using superposition theorem? First is to eliminate all but one source. This step is subdivided into two: the voltage sources and the current sources. All voltage sources are shorted while the current sources are now opened. So step number 2, use series parallel analysis to determine voltage or current drops. In this step, as you retain one source, you will now use series and parallel analysis in solving the electrical parameters of a particular electrical component. So step number 3, determine the flow caused by each source. In this way, you will now be able to know how each source affects all the electrical components, which can be really helpful in solving the problem. So step number 4, get the total voltage or current. Take an example on how superposition theorem works. So let's take the circuit. Okay, in this problem we are asked to find the amount of voltage flowing in the 6 ohm resistor. So before we begin, as I have said earlier, all voltage sources are shorted while the current ones are open. So as you can see, there are 2 voltage sources present in the circuit, the 33 volt and 11 volt. So first, let's consider the 30 volt source giving us this circuit. Okay, as you can see, the 11 volt source are now shorted, which leaves us the 6 ohms and 3 ohms parallel to each other, which is now equal to 6 times 3 all over 6 plus 3 equals 19 over 9 equals 2. Therefore, R23 is equal to 2 ohms. RT is now equal to 9 ohm plus 2 ohm equals 11 ohms. So, putting sign conventions in the 6 ohm resistor. Therefore, by using voltage divider theorem, you can now find the amount of voltage flowing in the R23, which is now equal to 30 volt times 2 all over 9 plus 2 is now equal to 6 volts. There you go. So since in parallel circuit here, the voltage flowing in the resistor 1 is also equal to the voltage flowing the second resistor. Therefore, V is equals to 6 volts. So second, let's now consider the 11 volt source giving us this circuit. Okay, as you can see, the 33 volt is now shorted. So 9 ohm is now parallel to 6 ohms, which is now equal to 9 times 6 all over 9 plus 6. It is now equal to 54 over 15 or 18 over 5 ohms. Therefore, the amount of total resistance flowing the circuit is now equal to 3 plus 18 over 5 or 33 over 5 ohms. So by using again the voltage divider theorem, so V at 213 is now equal to 11 times 18 over 5 all over 30 over 5, which is now equal to 6 volts also. Therefore, at 33 volt source, the amount of voltage flowing at 6 ohms is equal to 6 volts, while at 11 volt source, the amount of flowing at 6 ohms is also equal to 6 volts. So let's draw the circuit first. There you go. As you can see, the flow caused by the sources is like this. Therefore, the total voltage flowing at 6 ohm resistor is equal to 6 volts plus 6 volts, or simply 12 volts. There you go.
The next topic to be discussed is about mesh analysis. This mesh analysis is an alternative method that is sometimes easier to apply to certain circuits. It is termed as loop analysis, but normally called as a Maxwell method. So today I will give you a certain circuit which mesh analysis can be applied. So I include two sources which is 7 volts and a 6 volts, a 5 resistance which is 2 ohms, 1 3 ohm, and 1 2 ohm. I will assume a circulating current I1, circulating current I2, and circulating current I3. So I will take KBL at loop 1. So negative 7 plus 1 quantity I1 minus I2 plus 6 plus 2 quantity I1 minus I3. The simplified form is 3I1 minus I2 minus 2I3 equals 1. We take KBL for loop 2. 1 quantity I2 minus I1 plus 2I2 plus 3I2 minus I3 equals 0. The simplified form is negative I1 plus 6I2 minus 3I3 equals 0. KBL for loop 3. 2 quantity I3 minus I1 minus 6 plus 3 quantity I3 minus I2 plus I3 equals 0. The simplified form is negative 2I1 minus 3I2 plus 6I3 equals 0. Solving simultaneously equation 1, equation 2, and equation 3, we will get the value of I1, I2, and I3, which is I1 is equals to 3 ampere, I2 equals to 2 ampere, and I3 equals to 3 amperes. So I1 is the certain current, I2, and I3 that we assumed earlier. Next, we were going to solve a special case in Maxwell method, which is called a super mesh. This is a two meshes that have a current source as a common element. The current source is in the interior of the super mesh. We thus reduce the number of meshes by 1 for each current source present. If the current source lies on the perimeter of the circuit, then the single mesh in which it is found is ignored. In this circuit, the 7 ampere source is our super mesh. Just like before, we will going to assume circuiting current I1, I2, and I3 in each mesh. Doing the same thing with the KBL for loop 1, and we will get negative 7 plus 1 I2 minus I2 plus 3 I3 minus I2 plus I3 equals to 0. The simplified form is I1 minus 4I2 plus 4I3 equals to 7. KBL for loop 3, 2 I2 minus I1 plus 2I2 plus 3I2 minus I3. Simplified form is negative I1 plus 6I2 minus 3I3 equals to 0. Taking KCL point x, we will get I1 minus I3 equals to 7. Equation 1, equation 2, and equation 3. Solving simultaneously the equation 1, equation 2, and equation 3, we will get the value of I1 which is 9 ohm, I2 which is 2.5 ohm, and I3 which is 2 ohm. And that's all about Maxwell method.
Now I'll be discussing the source transformation method. So, source transformation method is another tool for simplifying circuits. So this method utilizes the concept of Ohm's law in order for us to fully understand a given circuit. So this diagram shows how source transformation works. We can observe in figure 1 that the voltage source is connected in series with the resistor. So we can actually transform the voltage source into a current source as shown in figure 2 by the help of Ohm's law, which is stated by the formula R is equal to V over I. So this process can work vice versa. So this is for the resistance and this is for the current. Same process works with dependent sources. So I got the A and B, the R, Vs, and the arrow here, dependent source, the resistance, A here and B. So this is for the dependent source and this one's for the independent source. Now, in assigning the direction of the current source, we should only remember that the arrow should always point to the positive terminal of the voltage source. So plus minus here, then downwards, upwards, and minus plus here, and it is downwards. Now let us try this example. So our example is a DC circuit which is composed of the following resistances. So I got here 5, the 6 ampere, the 15 ampere here, the 6 ohms, the VO, the 24 voltage here, and the 4 ohms. We are going to compute for VO. So first step will be the source transformation. So we can observe that this part and this part satisfies the condition for source transformation, so we can use Ohm's law. So the Vs, which is equal to 5 times 6, will be 30 volts, and the I, 24 over 4, will be equal to 6 amperes. So now for the second step. So we're going to redraw the circuit here. So I got here the minus plus here, the resistance, another resistance, and then another resistance here, and finally the current source. So I got here 30 volts, the 5 ohms, the 15 ohms, 6 in VO, 4 ohms, and the 6 amperes. So this part satisfies the condition for source transformation, but these, we can see that these two resistances can be added, so it is equivalent to 20 ohms. So now we can apply again the source transformation here on step 3. So in this part, we're going to use Ohm's law, which is Is will be 30 volts over 20. So our Is will be equal to 1.5 amperes. Now, step 4. We must redraw again the circuit so that we can understand the problem. So downwards is 1.5 ampere, the 20 ohms here, the VO here, 6 ohms, the 4 ohm here, and the 6 ampere here. So we can see that these two current can be combined, and also these two resistances. So combining those components, we can come up with a I total, which is 6 minus 1.5, because 1.5 is downwards, so it will be equivalent to 4.5 amperes. So the resistance will be the parallel combination of 20 and 4, so it will be equivalent to 80 over 24 or 10 over 3 ohms. So for step 5, I'll be redrawing the circuit again. So I got the circuit here, and the resistance is here, and the current source here. So I got 10 over 3, the 6 ohm, the VO, and the 6 ampere. So, oh, I'm sorry, I forgot. It's 4.5 amperes. So it is upwards because 4.5 is positive. So we can observe that the VO here is not changed because it is the one that we're going to find. So by applying current division, so to get the current on the 6 ohm resistor, it will be 4.5 times 10 over 3 all over the summation of the remaining resistances, which is equivalent to, wait, I'm typing it on the calculator, and it is 1.6071 amperes. So it will be the current on our 6 ohm resistor. So applying Ohm's law to find the V or the VO. So 1.6071 times 6. So now it will be equal to, so the calculator says that it is 9.6426 volts. So that will be our final answer. That's it.
A method that provides the nodal voltages of a network, meaning the voltage from the various nodes of the network with respect to the ground. This method is developed through the use of Kirchoff's current law in much the same manner as Kirchoff's voltage law was used to develop the mesh analysis approach. Although it is not a requirement, we make it a policy to make ground our reference node and assign it a potential level of 0 volts. All other voltage levels are then found with respect to this reference level. For a network of n nodes, by assigning 1 as a reference node, we have n-1 nodes for which the voltage must be determined. In other words, the number of nodes for which the voltage must be determined using nodal analysis is 1 less than the total number of nodes. The result of the above is n-1 nodal voltages that need to be determined, requiring that n-1 independent equations be written to find the nodal voltages. In other words, the number of equations required to solve for all the nodal voltages of a network is 1 less than the total number of independent nodes. Since each equation is a result of an application of Kirchoff's current law, Kirchoff's current law must be applied n-1 times for each network. But before applying nodal analysis, let us define node. Node refers to any point in the circuit when 3 or more circuit elements meet. For example, in this circuit, this is node 1, then the node 2 where 4 elements meet, and the third node which is the node 3. So the total node is 1 plus 1 plus 1 is equal to 3 nodes. Nodal analysis, like mesh analysis, can be applied by a series of carefully defined steps. The examples to follow explains each step in detail. First, determine the number of nodes within the network. Second, pick a reference node and label each remaining node with a subscripted value of voltage V1, V2, and so on. Apply Kirchoff's current law at each node except the reference. Assume that all unknown current leave the node for each application of Kirchoff's current law. In other words, for each node, don't be influenced by the direction that an unknown current for another node may have had. Each node is to be treated as a separate entity, independent of the applications of Kirchoff's current law to the other nodes. So step 1, we determine the number of nodes. There are 3 nodes, the node 1, the node 2, and the node 3. For step 2, we will pick the reference node at the ground, which is the node 1, node 2 for V1, and lastly node 3 for V2. Step 3, we apply Kirchoff's current law at each node V1 and V2 and apply Ohm's law
Preview. Instrumentsbackgroundmusic.com.
But there's an easy way to solve this circuit using format approach. But make sure all sources must be converted to current source. First, choose a reference node and assign a subscripted voltage label to the n-1 remaining nodes of the network. The number of equations required for a complete solution is equal to the number of subscripted voltages n-1. Column 1. Column 1 of each equation is formed by summing the conductances tied to the node of interest and multiplying the result by the subscripted nodal voltage. We must now consider the mutual terms that are always subtracted from the first column. Each mutual term is the product of the mutual conductance and the other nodal voltage tied to that conductance. It is possible to have more than one mutual term if the nodal voltage of current interest has an element in common with more than one other nodal voltage. Fourth, the column to the right of the equality sign is the algebraic sum of the current sources tied to the node of interest. A current source is assigned a positive sign if it supplies a current to a node, and negative sign if it draws current from the node. And lastly, solve the resulting simultaneous equations for the desired voltages.